Thank you for having me back. Thank you for having me out here in 2018 because this project really was an outgrowth of that. I was on a sabbatical that year, and this was one of the main things that I did with that time, and my wife challenged me to pick 3 things. I had this list of like 12 things I was going to do on sabbatical, and she's not an academic, but she knew that was not going to work. So she narrowed it to 3. She said, come up with 3 things, and one of the things that made my final 3 list was learn something new. So I was coming here in logic and group theory, and so I thought I'm going to learn logic. And you'll see how that turned out, if you'll disagree entirely, and that's all right. But let's start with something simpler. I think most of us probably heard this story before, but if not, you can watch this little YouTube video by some blogger, Veritasium is his channel, and they make interesting stories of various topics, including mathematical ones. So back in 1545, let me see if I can pronounce this here, Tartaglia, is that better? So Tartaglia and Cardano face off on a duel. This is the most nerdy duel you can imagine. You give each other 30 polynomials and you have to factor them, and the winner is whoever has factored the most. It's worthy of a YouTube channel, apparently. Why am I bringing this up, though, is the question that I want to ask about this is, why is this even a competition? Why is this even something you can actually make a competition out of?
They didn't have Mathematica in those days.
Oh, it's true. I mean, but they did have, you could up the degree of the polynomial to something that would still outdo mathematics, perhaps. But I think there's a better reason from my perspective, which is that you can check the answer. I don't have to give away my strategy, and you can still see if I won. So if I've got up a really killer strategy, which both of these gentlemen did, they both found out how to factor the cubic. This is before we even knew about things like that every cubic had exactly 3 roots. So imagine that you don't even know that, and you're competing this way. Now we know so much, it doesn't feel that challenging, but back then the technology was different. But you could check the answer. You could just put them on 2 sides of your area, multiply them out, you get the balance, and they're equal. That's what they were thinking about. It was balancing areas. That's back to Al-Khwarizmi's methods of algebra. Method of balance is what that means. Who won this competition? Anybody know what happened? You watch the video, but it turns out they just ripped up each other's solutions and insulted each other. They did not like each other at all. They refused to believe the other person was worthy of checking, and yeah, that's why we know about them. So I like this idea. Oh, what's a modern version of this competition, and why is it getting harder for me? This is, the 5 of us all have this problem. We're faced with just a whopping number of groups out there. Billions of groups are in the data tables, or at least we know of the existence of, even up to small sizes like 2,000. Groups come with all these extra pieces that are going on. There's so many of them, and if we want to keep our funding, then our job is to somehow come up with isomorphism solutions, automorphisms, and that's our challenge. Just what I named them all once. That's me, that's Eamon, he's back here. Josh Maglione, he's at Galway University, is that the right name this year?
Galway.
University of Galway though, right? It's not...
The University of Galway.
Right, the name keeps changing, so I apologize. That's not my fault, that's universities. Peter Brooksbank is at Bucknell, and Heiko Dietrich is at the back, he is at Monash. Okay, so we've been working on problems like this together and on and off. But there's some really good challengers from a long time ago. Ada Rotlander is one of them. Yif is another one. There's several, but this is just the one I like the most because it's the first math paper I read. The professor wanted to shut me up from asking questions in class, so he said, oh, go read this paper. It was in German. I didn't know German. Still don't know German.
He didn't shut you up.
Did not shut me up. Hasn't worked. One mistake that I noticed, that's not a 2, that's an E right there. So, and that is also an E. Excuse the handwriting of this font. Okay, so if you look at this, you say, okay, there's a group anyone could be taught in elementary school. Well, I have to know what Z mod P is. So we don't think of this as a challenging group. But here's the challenge. Here are 2 subgroups. So what I mean is you just put any value of Z mod Q in here, any value of Z mod Q in there. Here are 2 subgroups, and the answer is that these turn out to be characteristic, kinda, sometimes. When? Well, you have to look at which P and Q you have and which A and B you have. And sometimes they are, and sometimes they aren't. And if you want to just check out now and figure that out for the rest of the talk, that's fine, okay? But I would ask you to play by some rules. The whole reason we, the 5 guys, want to have characteristic subgroups is because we want to build automorphisms. So what you can't do is prove their characteristic by computing all the automorphisms and then discovering that it doesn't move those points in some situations. You've got to come up with a reason these are characteristic that is different and external to that, which is why it's a hard problem. We don't even know how to check if something is characteristic without the automorphisms, because we define it with the automorphisms. So if I just tell you it's characteristic, how are you going to prove me wrong? You'd have to go find some automorphism that moves it, and we don't have them. So unlike Tartaglia and Cardano, you can't check our results. So this is how we get grants. We just tell them we did it, and they don't know. It gets worse if you make it bigger, and these are still on the baby side of group theory. If you try to do some, let's call them grant grade groups, they're going to be even worse. Just the way that characteristic subgroups show up, and you have no hope of understanding their automorphisms, and you're still supposed to determine that they're characteristic so you can use them in the next stage of an algorithm. So I suppose I should tell you a little bit about algorithms for finding automorphisms, so you can see how this is built in the secret sauce. There are several variations on this. This is my abstraction of multiple methods, how I think of it. If you don't see your method in here, it's because I didn't value it as much as my own. It's just, I'm simplifying to what makes a story. Oh, I should just tell you in broad strokes. There's some stage which, without being pejorative, it's an ad hoc mix of different tricks. Try some things out that your intuition tells you, or that the story problem tells you, that subject matter expert tells you. I think that the Thompson subgroup's important for this, whatever. You pick some things that you start stuff out with. Those are the seeds. Then you go off and do some calculations, which are meant to organize that and build a structure you can compute with. Basically, you're trying to turn everything into linear algebra, everything you can. Then you go off and do some Lie theory, which is linear algebra for grown-ups. And then you come back and put it back on the group. So if that's all you want to know, then you have it there, but I'll go through it in more detail. Some of the obvious choices for characteristic subgroups have names. They go way back to the beginning of time. Time started with Cayley. Centers, commutators, different power maps, and so forth. They give you things that you probably teach in your classes or have used yourself. Harder ones show up in the early 1900s with fitting subgroups and so forth. Philip Hall worked hard to sort of bring some of them together under some classical names that we now know as verbal and marginal subgroups. Depending on where you are in the sort of slow slide towards simple-minded group theory, you might know some others, like Glauberman subgroups and Alpin subgroups and stuff like that. After the named ones, then you have the hunting, right? You decide not to name them after things because they're going to be so ephemeral. They're going to apply to this very narrow class of solvable groups or something. And so you're really just looking for algorithms that can, by the nature of what they run, whatever they return will be characteristic. Already I'm moving into the murky. What do you mean by the nature of how they run, they're going to be characteristic? Something has to be said there that's a little bit stronger than what I said. But it's hard to put your finger on what you should say when you're first coming up with these ideas. So there's all sorts of graphs you label, and you look at intersections of sub things and centralizers here and there. And it's remarkable how many characteristic subgroups show up by ad hoc methods, by things that have never been named. Like the ones that are above here almost never serve in isomorphism testing. They just aren't meaningful. They're like trivial, or the center is the same as the commutator, is the same as the Frattini, is the same as the everything. So you learned one subgroup. So these methods turn out to be a place where you get a lot of information by doing several different techniques, and they span a bunch of different strategies. Once you have them, then you want to sort of iterate. Start taking commutators of things that you know, start taking centralizers, put them in graphs, label the graphs, take the, all the colors are the same. On a graph, you've labeled them all as blue, or some vertices as blue, take the subgroup of all blues, that's going to be characteristic. And so there's a bunch of strategies that have been explored. In particular, Josh Maglione deserves mention there for having made actual software out of the imagination of the others there. So, imagine now that you have a strategy for collecting some characteristic subgroups that are motivated or unmotivated, they've come to you. We're now going to put them together to do linear algebra, okay? So here's a strategy that maybe is obvious, but it's difficult to find treatments of this that bother to study it as a theory. So I think all of us do the following steps in some informal way. I'll just mention, you could make this formal and you might actually accelerate some of the things you do in practice. Start with a commutative preordered monoid. If you don't know one of those, just take the natural numbers to some power. You can put a, Lex order on it, you can put pointwise order, lots of different orders will work. But whatever, let's start with some example. And then you take a function from that monoid into the subgroups of your group G. Make it order reversing, that's that last rule. And then this last part here is to say that you want it to be aware of some of the group theory. Just how do the commutators of those subgroups work? If you take the commutator of phi s and phi t, that should be inside of phi s plus t. So that tells you somehow how that lattice is moving down in the product, okay? You get a boundary filter. If you're at some point, you take all the things that are dangling below. Bind them together, call that the boundary. I'll do a picture in a second where we see it worked out. It turns out that from the commutator relations, if you take these things, this filter, well, first of all, that'll be a filter. It'll be normal in the previous one, so you get these little sections. Those sections will actually be abelian groups. You sum over them, you put the commutator bracket back on all those pieces, and it makes a big Lie algebra. What about that top one where things kind of do a little bit different? Think about that as like, I have a nilpotent radical, and then I have some kind of maybe bit of extra solvable, maybe some simple groups, stuff that isn't going to filter into Lie algebras. That just adds to your module theory. Everything becomes a module over that stuff, and so you have this nice module theory. You have a Z, whatever that thing is, Lie algebra. Okay. Is that roughly sensible? If you want to ignore all this, take the lower central series of a group, take gamma 1, mod gamma 2, mod gamma 3, so forth, and take the usual associated Lie algebra. This is that done in generality. Bottom up, you can take the lower central series and come up. Sometimes it's easier to get groups at the bottom than at the top. You do this all in reverse order. You get a co-grading instead of a grading. That means that you sort of have the S minus T business going on here. That turns out to make a module for that Lie algebra. It's just the same sort of thing that you see in Poincare duality of cap and cup, right? It's that same standard thing where you have a Lie algebra and you have a Lie module and you make them talk to each other. All right, let's see it done in a picture. Here's a bunch of subgroups in a group that I love. Group that showed up in my thesis. You don't have to know what it is, but it's a group, and it's got a lot of subgroups going on. So you could pick these three as kind of your initial starting points. It turns out this group happens to have 3 characteristic subgroups that have these various names. And then you generate the associated filter from this by sort of taking commutators that are missing and put them in and label them according to how the monoid would say S plus T must go here. And you keep doing this. You might pick up relations. For example, you might have 2 of the arrows go to the same place at times. That's why you start collapsing your n cubed. Your standard grid starts to have these degenerations at some point. This is why you have to generalize to monoids. Build out this whole lattice over time. Okay. Again, doing this efficiently and so forth, there's concerns, but I won't talk about them. Okay. Is it sort of sensible? Now the key thing is that every edge here is an abelian group. And then we're going to take all those, let's call them vector spaces. Just call them vector spaces, it'll be easier. Take all those vector spaces, add them all up, and you make this gigantic Lie algebra, but it's a vector space. So you can do arithmetic on it. Which takes us to this phase 2, or phase 3, sorry. Phase 1, get some place to start, those initial 3 things. Phase 2, spread it out as a nice coordinated lattice, make it a Lie algebra, so you can do the arithmetic you want. The Lie theory now shows up as a useful step here. Because, remember, our goal is to figure out whatever aught G is. And we don't have it. What we can do is start with our group, build this lattice, or build this filter of these abelian sections. So I have L star phi. I want alpha. What is alpha? If you look at alpha, it's a bunch of subgroups of the automorphism group. It starts with the full automorphism group, that's alpha 0. As I come out with every one of the directions of my monoid, I look for the parts that shift by +1, or by +s. Now shifting doesn't make sense. Automorphisms don't move things like they're isomorphisms, right? So I'm going to send a subgroup back to a subgroup of the same size. So what do I mean by shift down? Notice I put the x inverse at the end there. So I'm taking the commutator in the holomorph group, if you like. Okay? So I'm shifting somewhere else, and that gives you a filtration on the automorphism group. Now, I don't have the automorphism group, so this is all just, in theory, there's a filter out there. But I'm lifting the filter to the whole automorphism group so that I can state what must happen. The automorphism group is now filtered, so it has a Lie algebra L star alpha. That Lie algebra embeds in the derivation algebra of the Lie algebra that I have. Derivations are a linear system of equations. I have a giant vector space. I go compute. Now, it's a big system, depending on your filter, but you have linear algebra, is really good at scale. So I go off and I can compute dir of L star. And then my goal is to pull back to the unknown L star alpha to learn about my automorphism group. For example, if all you want to know is the order of the automorphism group, if you can do this, you can get the order. You don't have to compute alpha at all. You don't have to actually compute the automorphisms. You can just multiply the layers of the L star alpha, just to give you a sense for what you're learning from this. So this is my perspective on what we're doing when we linearize. Now there's lots of individual techniques that peel off just a piece of this instead of the whole artifact. That's fine. The P quotient algorithm is doing something like this, or the P multiplicator, that's a piece of this derivation algebra. You can put those stories inside this, I claim.
Just to make sure, right? The derivation algebra is computable, but like the image of this equation is not computable.
Yeah, because I don't have, well, actually, it's decidable. So to the extent that you can reduce to that, yes. But I'm not saying that's an efficient test. I'll put that on, that's step 4. I'll explain what that's the Evanios-Chow technique. Not necessarily as efficient as we want, but it is desirable. You can do a dual version, work with a Lie module, if you know that you're coming from the bottom, use the sediments. Okay, let's try to see this out in some kind of schematic diagram here. So the target is to know about F, which is the whole automorphism action of some unknown thing, and I work out derivations. The things that I have on these diagonals, that's the module theory. I have to do that separately. I have to do G mod, say the fitting subgroup, and that piece goes into my module theory, and you just have to do representation theory of simple groups and stuff like that. Sorry for all of you who think that there are non-nilpotent groups. That's your problem. So for me, that's all 0. Everybody else then, all the other automorphisms, are shifting the grading, aren't they? There we go. So they move up in this, right? So this here, F12 is sending L1 to L2, and so forth, just moving down. If you prefer to see these as automorphisms, then you just do the exponential of this, put 1s there, that kind of a thing. It's not done as the exponential, I know, right, yeah, division by 0 problem, but that's the second order problem which can't be solved in this situation. If you move to the second part of this layer, you're shifting 2, so forth. I think you know what I'm doing here. I'm just trying to say we're linearizing the action of this group by saying the upper triangular bits are the stuff where the filter of alphas is helping us learn about it. The stuff on the diagonals where all the simple group theory happens. So we're just compartmentalizing. We're just shoving off jobs to different people. Okay? All right. And the last part, which I'm not talking about in this talk, is that pruning algorithm that Martin was asking about. And this is as efficient as it is. This needs work, right? This is going to run through all the actual vectors in that vector space, and it can cut it down. This test is sort of a 2-part test. It works on the groups that you can list things for, but this is why we aren't better than O of the order of the group and things like that. Like the complexity of group isomorphism for finite groups is if a group has order n, then it's n to the log n. Maybe you can fuss about some constants. That's a bound that basically says brute force. Just try every generating set. Generating sets have size log n. Just match every generating set up until you find the automorphisms. If that's the thing you're competing against, you've got to feel as a group theorist we could beat that. And yet here we are, 60 years later, having done nothing. And so we're trying to compete with that. So even if you just bring this down to a constant, which is what this test can let you do, that's better. I would love to get it to a real lower bound of some logs down here, but I'm not there yet, neither are you. Well, if you are, let's have lunch. Okay? Not going to talk about that black box, but it's out there if you want to read about it. So, summary, if you're looking at automorphisms, you start by your favorite or cooked up or strange, rare, whatever, your ad hoc characteristic things. You filter to organize it into a bunch of vector spaces. You do some linear algebra. You cut back with a test that we'd love to improve, but it's not the topic of today. What happens if we were wrong about our characteristic subgroup? So that is gone. I thought it was characteristic, but I fooled myself. And because I don't have the automorphism group, I don't know how to check that right now. You could hope that you just run the algorithm, and at the end you check your answer. The trouble is that that's no longer a characteristic filter. And so the theorem about lifting doesn't apply to the automorphism group, it applies to some other group. And so what you'll get back out of this method is some other group. And that other group will confirm your earlier suspicion that it was characteristic, because it was designed to keep that space invariant. So there's no background test. You can't run this and at the end correct yourself. You will fool yourself. So you can't get that first step wrong, otherwise the whole thing falls apart.
What's imposter mean? I don't understand that.
An imposter would be somebody that claims to be characteristic but isn't.
Oh.
I don't think that's a standard use name. That might be a Wilsonian use, the word imposter. I'm not known to actually understand the English language. Some of that is showing up today.
You know, imposter is pretty.
Would it be fair there?
It's a real word.
Wonderful. Is it spelled that way?
It's a real syndrome.
We're in a better place than I thought.
There's plenty of us who suffer from it. Fake characteristics subgroups. Fake characteristics.
Fake, yeah. I mean, I could have said something classy like pseudo characters. That is a chalkboard upstairs, if some of you recognize it. About this time, these ideas are kind of around that era, a little bit before, and I was invited to this workshop here to learn about logic and group theory, and so I did what all of us would do. I went to Google and said, what on earth is logic? And it sent me to NLab. Now you could say that's where everything got off the rails, because if you've been to NLab, this is like a modern day Bourbaki with a lot of attitude, right? I mean, it's got an opinion that if you want to know what a group is, you start by saying it's a category in which, like, wow, okay. So this is what happened because of that. I'm introducing you to that monstrosity that is roughly the way some people interpret the result that I'm going to tell you about. It's a mixture of a lot of different ideas trying to tangle with the question of how do I check that something is characteristic when I don't have automorphisms. And I'm going to do something that seems absurd. I'm going to make the problem harder in order to solve it. Okay? And it's a mixture of category theory, type theory, and some model theory, universal algebra. It's just a bag of tricks. And I'm going to try to make that sound like it was a principled, smart thing to have done from the beginning, but that's storytelling. We just tried it, we refined it, and we got it to work, okay? So here's what we are really doing. Oh, actually we did. We managed to keep some of the grants, and then something happened in the US. So we'll see about that now. So let's go back to the definition of characteristic. I know you all know it, but I want to pause and think about it differently. H is a subgroup of G in which every automorphism of G sends H back to H. Allow me to write it in this somewhat ridiculous way and say that H is included into G by some inclusion homomorphism. Sends H to H, of course. And that instead of talking about phi of H equals H like a set theorist, I'm going to try to talk like a category theorist. I'm going to say, well, I have a homomorphism phi here, which restricts or induces a homomorphism between the H's. Okay? That's the same sentence, just written in a categorical language. But it's a selfish sentence because it just talks to itself. So I think that the word group tells you what you should do. Groups are fond of the company of others. So you should not start with one G, you should have two G's. And you should talk about an arbitrary homomorphism between G and G tilde. And so what you should really be asking is, if I have two isomorphisms going to wherever they go, they should send H to the same place. Now that recovers this as a special case, but it turns out to be equivalent, because you could just move the inverse of, say, C to that side, and then you're talking about characteristic. Okay? So these are equivalent, but this one is much more categorical, in that now you're talking about all the morphisms in some larger category. Now you could go back here and say, actually this was a category too. This is the category of all automorphisms of G. That's the category of automorphisms of H. So let's try to put that language together.
Sorry, James.
Yes?
I have a bit confused with the picture. Where is the C?
In this one I only have phi, because I'm just trying to show you where the image of one restriction goes, but you could put another C here, and the point is it would also restrict to the same place. They wouldn't be the same function now, but they would be the same place, the same signature.
Thanks.
If you spend enough time on NLab, you come away with something like this. This is not on their page. I'm very proud of my TXT skills. That's why this is in the slideshow. This was pre-ChatGPT, and now I realize I could have spent about 5 minutes instead of 5 days. But there we go. This is how I think of categories after spending too many nights on NLab. Forget about anything being anything. There are no objects. These are just placeholders for how you're going to compute with the arrows, right? That's the whole idea. So what do we have is we have a very basic algebra. If we're in one of these kind of little f's, you might call that a functor, but then your brain is probably thinking about doing something like a function. Don't. It's just a piece of data, and x is some other piece of data, and it has the following algebra. F times x is just some other object. F times an arrow is just some other arrow. F times commuting diagram of arrows is just some other commuting diagram of arrows. So a point doesn't change the complexity of that diagram. Now you come to this double arrow one, and you probably heard the word natural transformation, and I have to say, when I was a student, I tapped out about right there. Like, okay, I don't really see how this is going to help my life. Yeah, murmur, lots of definitions, lots of pictures that we're all going to get wrong, and it hasn't improved my life. I check out here. I'm going to ask you, if that was your experience, to come back for just a minute and just think of it syntactically. Think that whenever I have a double arrow, I'm just telling you how I'm going to act on other data. And in particular, a double arrow means if it meets a point, like x, it turns into a single arrow. If it meets another arrow, it turns into a commutative square. If it meets, say, that commutative triangle, it turns into the cylinder. If that's all it does for you, that's enough. Let's go back to the picture that we're looking at. This one here is a little commutative square in which I see the data is labeled such that it's kind of dependent. These horizontals, I should have a tilde on it, these here are kind of dependent on just that piece there. So maybe they factor, whoops, like this middle square, where there's an F and a G business. Now, I told you I was so proud of my TXT skills. They do not extend to transposing this picture. So the picture on the previous slide and this picture are in the opposite orientation, so you'll have to do that part in your own head. So here it is. The natural transformation is on top instead of the side in this picture. C is just my name for the characteristic subgroup I want to talk about. If you want an example, think of the center. The center is a subgroup of every single group, right? So when I put the example by Ada Rotlander, I had one group, and then I had this spurious example of this one subgroup, and I said, is that one characteristic? It was hard to know. But when I say the center, I'm telling you something much more profound. I'm telling you every group has this other group and behaves in some predictable way, group theoretically predictable way, and that's what a functor does. A functor says, I'm going to tell you what to do to anything in this category consistently. And that's a different way of talking about characteristic than saying, here's a group that just doesn't move under its automorphisms. Right? By being gregarious instead of selfish, we learn what really is going on in the world of centers, which are easy to prove as characteristic, versus the Yif and Rotlander examples, which no one has a clue why they're characteristic. I'm going to abstract the thing that I'm getting as a category notion of a functor applied to the group, and the natural transformation as the way I embed the one into the other. This comes with a lot of extra baggage, but it has a lot of advantages too. For example, the first thing you learn in category theory is that you get credit for just turning the arrows around, right? Like free homeworks. You do in class all the arrows pointing left, and you make the homework all arrows pointing right, okay? And so what's the arrows pointing right in this case? These are characteristic subgroups. What would it dualize to? It rhymes with characteristic quotient, right? Now that might feel like, look, group theory spoils us, right? You think, look, you can talk about the kernel of a homomorphism or the homomorphism, what's the difference? Go to ring theory. The Jacobson radical is not a subring, has no one. There are many algebraic theories where there isn't the duality of kernels that way. Kernels become a congruence in some congruence relation, they're not in the actual algebra. Okay, so plenty of situations that have characteristic quotients do not come from characteristic sub-things, all right? So you do have to have a split theory. That duality matters when you leave the world of group theory. And I won't do it explicitly, but everything I'm saying here today has no interest in group theory at all. It applies to any algebraic theory. There's a few technical glitches. Those of you who do enough category theory have seen it. Over here, I really wanted to talk about isomorphisms, and inclusions aren't very isomorphic, are they? Right? Not if it's an interesting characteristic subgroup. So we actually are writing the sentence outside of the categories we're interested in, and that causes us to write a slightly more complicated picture. Over here, this is the selfish version, automorphisms of the group talking back to themselves. Automorphisms of the subgroup talking back to themselves. The functor said, anything that I do here, I can restrict. So it left the category aught-G and went to the category aught-H. The knitting them together, that little commutative square that I wrote, is saying that all of that takes place in the category of groups. That's what this picture is trying to say. That double arrow, I mean, category theory was invented by algebraists but has been taken over by topology. Absolutely so. So everything here has cellular kind of notions to it. So you put a 2-cell on to talk about it as like the way that you're deforming this composition of functors to that composition. Okay? And there's value added to that. The gregarious point of view says, I want something like the center that applies to every group. Everyone needs to have a center, or everyone needs to have whatever that Rotlander example was. You can't just give me one group with it. Everyone should have a corresponding Rotlander subgroup. That says that you don't start with aught-G to aught-H, you start with all groups to all groups. Okay, the little arrow thing up there is saying, just give me the isomorphisms, what's called the core subcategory. So there's a little bit of restriction here, that's why there's inclusion functors, technicalities. If you don't want the technicalities, replace the words with fully invariant. Characteristic is just automorphism invariant, fully invariant is any endomorphism. Then you get a simpler story, you have group to group. This is the subs thing that you want to keep preserved, like the commutator. That doesn't change even under homomorphisms. The center certainly does, but the commutator doesn't. And so if you just take the commutator as your leading example, you get a simpler model of this story. Simpler type of natural transformation. So whichever one you like, that's your business now. And here's the first effective theorem of this. I don't expect you to look at this eyeball and think, that's pretty. But I want you to maybe respect the fact that this is the simplest way that we have found to date to express what we mean by finding a characteristic subgroup like the center. Meaning it's a characteristic definition that applies to everybody in the category in a way that you could then apply for isomorphism testing, automorphism testing, for any kind of algorithm that you want to do. That you could verify that it's characteristic without having automorphisms. And without maybe detailing too much, what this picture is saying is, if I went from the automorphisms of my group G to the automorphisms of my subgroup H, and made them do that commuting square, that's what the definition of characteristic is, there's always some other extension to a particular subcategory. I'm not detailing what, but basically think of it as the invertible the invertible homomorphisms in the category of groups. I can always build and extend that functor to everybody and make that characteristic globally. So now if I do this extension in a practical way, then I don't talk about Rotlander's subgroup of that group G, I talk about Rotlander's subgroup of arbitrary groups, like the center. So it's this, I don't know what that color is, salmon? The salmon color there is what we really think of as like the center being characteristic, and the blue is what we think of as a specific subgroup being characteristic. And this is saying you can always do this. Okay? So that says there is an answer to be had. Is it attainable? This is what I said I was going to make it harder so that I could solve it. Okay, well, the harder part is that now I have to what? Talk about the category of all groups. You gave me one group to investigate, and now you say, oh, my solution is to talk about all groups instead. This is maybe a bit of a cheat. So how is it not a cheat? Or how do you make it not a cheat? So let's go in a little bit more deeply into what you need when you want to talk about a category. I think all of us have some walking around notion. Categories have their objects. They have their morphisms, they have this associative composition, they have identities. You'll probably get all those definitions correct. If you write down, and you're just honest with yourself, on your flight home, your train ride home, you just say, can I write down all the axioms of a category? I find that I often, and I think most people do, omit some, if not all, of the things on this list. In order to state the axioms of a category, there's one axiom which never gets in the books, and that you won't get off the ground if you don't do it. and it forces you into some set theory conundrums. You need to have disjoint Hom sets. You can't have this ambiguity of where my homomorphism lives, because then you don't have a well-defined composition rule. And when you try to extol what that means to people, I have disjoint. Well, wait a minute, this is in the category of what? So this is an impredicative definition. And it becomes impossible to write that without binding something to some small universe. You could say small categories, bring everything as a set. There's lots of things you could do to fix it, but the point is it's got to be fixed. And every fix that's in the books classically is very much against that idea. Which suggests that, okay, so you made a definition that no one can use because it's highly uncomputable. And that's not going to fly for us. So we're going to...
Is that the axiom of extension?
Oh, well, why are two sets equal if they have the same elements?
Extensionality.
Yeah, extensionality. Did I not type extensionality? Oh, yeah. Sorry. Ality, it's just very small. There's a really nice paper by Mike Schulman. I don't think it's been published. I don't think it's a publishable paper. I mean, you have to have one of these kind of discursive, type journals. But it says something like the set theory of category theory, the set theory you need for category theory. It's not that long. It's like 20 pages or something. And it just goes through thing after thing that you think, yeah, you should be able to do that. And it's just logically false. You end up with things like, take the union over all sets. Well, if that's not the set of all sets, what is? I mean, like, immediately you find yourself doing things that are ridiculous. And so then you start to realize, oh, I've been cheating. I've been thinking I knew what a category was the whole time. I have no idea. There is some smart people out there who've worked on solving it. I'm using a treatment that's by Peter Fried. It belongs to a lot of other people alongside. McLean did some of the work in this. This is the notion of an essentially algebraic theory. The idea is to somehow tame how the Homs glue together and not worry about gluing it all together as one edifice. That's the kind of the classical technique. Here, I'm going to glue everything together into one object A and make it have some algebra rules. So I turn this into a single model of one theory. And you have to do a little bit of extra work, and some of this is not written correctly in the literature. So I'm sort of proud that our group wrote it down correctly. And how do I know it's correctly? We have code. So anyway, some of that code is still in development, but we have a pretty good take on this now. The main thing is, you throw in a place to throw the garbage. This bot symbol is an artificial, extra-linguistic tool. I just add it to my language. Categories don't walk around with a bot. But we're adding it to the language of categories so that we can say what it means to be undefined. I don't know what it means to be undefined. I don't know if you know this, but if you type anything into a function in a computer, it'll actually do something. It'll probably insult you. It'll say, that's not a good input. But it does not stop you from putting 0 into the division function, does it? Right? This idea that there's undefined functions is a ludicrous idea. I don't know any computational model that has undefinedness. What it has is, I can tell you what the behavior is on these things, and outside of that, I'm not telling you anything. No promises outside of that. So let's promise that outside of that, you're going to do bot. So this is the sync rule, the top rule. If you put a bot into any of these operators, you get bot back. Once you fail, you stay failed. This one over here will be my codomain. That'll be my domain function. So everything in here is a morphism. There are no more objects in this category. They're all arrows. I ask for where does it end, where does it start, and can I glue two tails and tips? Okay? And if you check these rules that Fried came up with, it turns out they do exactly what you would get if you did it by other methods. But they don't deal with the set theory, because everything's put into one object A, and then you can just write this as a model for one language. All right, it turns out to be a variety, super fun. Example, this is to make the notation slightly more palatable for those of us who don't want to deal with all those other operators. You gather all the, what you might consider the identities, the traditional idea there, as some set of identities, and just call it mischievously the number 1, okay? And then it behaves like the number 1. There's a slight notational trick I'm playing here. So I have a set of identities of objects X, and then I compose it with, let's say, I'll be very careful here. Suppose that I have a function g from A to B. Then if I was to do this, it would be the identity on A. Right, saying what could come into G that wouldn't change it? Well, the identity could come into G and it wouldn't change it. okay? That's inside the set of all identities. And so when I compose it with G, I will get just G back, okay? So if this one is 1G as a coset, and this one is a set with just G in it, then allow me to cheat and just write G, so that it looks like an equation that I would use in a standard algebra class. It's just to simplify your calculations. You don't have to do this, you can go back and quantify this. But anyway, so that's allowing me to think of this as basically a monoid with a sink, a failure sink. Now that's a category. I can walk around with that description of a category. Just a multiplication that's associative, has a 1, and a failure state. So it's not that bad. That I can even put on a computer. It also tells me that I have a bunch of theorems that I can just go get off the shelf. Stacks of theorems are written about varieties and this kind of model, and we use them all in this paper. Not all, of course, we use a very tiny sliver. All the stuff in chapter 1 we use. Anything in chapter 2 is too hard. Here's the Peirce decomposition of this category drawn as dots and arrows, like the kind of pictures you would draw in a commutative diagram sort of thing. And what I'm doing here is I'm trying to tell you where the Hom sets are. So just like you would do with module theory and rings, you take idempotents, you hit the idempotent on left and right, and you make a little corner ring inside of you're trying to do Jacobson's coordinatization of rings. There's a coordinatization theorem for any monoid, and that's what this is doing here. This is the Peirce decomposition for this kind of maybe called a pseudo-monoid. It's not technically a 1, but a set of 1s. This is the layout that you have to tell Gap or Maglione how to do. You have to tell it how to multiply in these things here. The Hom is an emergent property rather than a starting place. All right. Well, what you do in a standard algebra course is at some point you make things act on things. It's an algebra, it can act on things. So let's have it act. An algebra A of this kind can act on a set X and do stuff. And it should do it just like what you think. It's an associative action, so it should be an associative action. The sink should stay as a sink. If you fail, just fail. And 1 should preserve 1. In that compacted Peirce decomposition, you get this nice matrix-looking product. The point x1 is sent by E back to itself. The point x1 is sent by H to the x2 position. The point x2 is sent to itself. It behaves like matrix multiplications. You could make this in a machine. So what does this unfold into telling you? A bunch of the things that you had to learn in category theory turn out to be examples of things like this in the algebra. My favorite is this very bottom one. If I have a category acting on another category, just like you would have a ring acting on a subring or something, or a subring acting on a bigger ring, that kind of a thing, you can make a notion of a left and a right action. And if you follow that through, the concept of an adjoint functor pair between two categories is simply to talk about a pseudo-inverse like you would in a linear algebra class. And I promise, if you write this down with the matrices, like that Peirce decomposition, you'll have this rectangle and another rectangle, they multiply to an identity. So this, to me, demystifies that weirdness that I always felt about, well, what does it mean for two categories to be adjoint? It doesn't mean they're isomorphic. That's a case when they are. But they could be non-isomorphic and still be adjoint, but I didn't have a feeling for what that meant. They're just pseudo-isomorphic, just like you had in a linear algebra class. That doesn't help you, I don't care. It helped me. Second theorem of this kind. Turns out that characteristic is not just anything in this. Turns out it's the representation theory of cyclic by, we call them capsules, but it's like the action. You act on the left and the right by the two categories. If you have a cyclic one, that's a characteristic structure. That's it. That's the complete automorphism-free description of characteristic. And it takes, I know this takes a lot to digest. It's a lot of language, but if you unwrap the layers, it turns out to be canonically what you should do. Like, this is chapter 1 stuff once you get through all the terminology. Once you have this, you also have a roadmap for how you could possibly compute with this stuff. Imagine that you are successful at creating an encoding in a computer algebra system of the category you want to study. Not the groups in the category, but the category of those groups, or the category of those rings. And you compute the representation theory of that category, and you find its cyclics. Then you're describing all the characteristic subgroups. I got asked in a talk, like, well, have you found any new characteristic subgroups? And I thought, I found them all. Not in a useful way, but like, this is This is what this is for, is to set us up with what is the target when we try to describe a characteristic subgroup now. It's to find these cyclic pieces of our actions. And because we've all sort of studied these things, where do you start? You start with a regular action. You start gluing it together with tensors. Well, there's a tensor. There's an induction restriction functor going on here. You glue, you break it up. Can you do that effectively? No idea. But some things we're starting to try. This needs a lot of work. So here are some general remarks of that kind. The dual version is about Jacobson radicals, that kind of thing. I already said that. Don't know about indecomposables. It's a totally obvious thing to try next, but I don't know what it represents, but it's something beyond characteristic. I have no idea. Are we missing some piece of group theory that we should have been doing? Is the algebra of the category telling us to go look some other way at the data we have? Maybe. But there's other representations out there that people can use, and they can go figure out what that means to the native objects in that category, and perhaps we discover we should have been looking at, I don't know, come up with a cool name for them. I leave that as a project for people who are interested. I don't know what to answer there. Pretty pictures. Let me try to put some worlds together. Everybody knows how to take the abinization of a group. We teach that in our undergraduate classes. We know that's characteristic. If you had to interpret it this way, this would just be an exercise in learning it. This would not be the most efficient way to understand the abinization. Please do not do this to your undergraduates. There's a homomorphism pi that goes from G to the abinization. That pi will serve the role of that natural transformation we're after. Notice it's not an inclusion, it's a surjection. That's why I said that duality matters. What's happening here is group is being sent to abelian groups and then embedded back into group. And the pi, natural transformation, is filling in that top cell. Okay? Then, when we talk about the derived subgroup as being characteristic, we're playing a special game that the category of groups is self-dual. Kernels land back in. So we take the kernel and it turns into a new, different directional natural transformation going from the bottom up, and that's the inclusion that is your lower central series term. Okay? So it's a two-step process to explain it this way, but you still get the one that you expected. If you look at what the thing is, it turns out that's a well-known pattern. That's an adjunction of group to abelian. And if you take an adjoint pair, you get one of these cyclic capsules. So anything that's adjoint is swept up in this. Immediately, everyone has a characteristic subgroup that goes with it, for free. Now go beyond. Look at something more general than adjoints. Here it is for varieties. Similar sort of story, so it doesn't have anything to do with the commutator subgroup. Any word would do. The marginal subgroups, they're much more fun. Here's the story for marginal subgroups. Philip Hall's marginal subgroups. So the center, if you don't know a marginal subgroup, think of the center, starting from the bottom up. Fun with Dixie. So you build the first thing, which is you take the isoclinisms, or isologisms if you're talking more generally. That's a thing. Look it up, Philip Hall. That goes back into group. Extend it. Take the kernels and expand. Not totally trivial looking. So let me try to write what you actually are going to look. These are pictures that help some of us think, but here's what it actually looks like in representation theory. Just tensor some stuff together. At some stage, we'll get to this level where there's a standard stuff you do. You tensor these regulars together, you decompose, you do whatever, right? It'll be standard stuff. We're not there yet, but that's what this says can be done. Here's a list you can't read, but it's just us trying to document what goes where, what pieces have been found. Okay, I'm going to wrap up with an attempt to talk about doing this in reality, in practical computation. Here's a slice of some of the code. Oh, no, that's on the next slide. I think of algebra as the computational arm of mathematics. If you talk to your PDE people, what do? They discretize and give you a linear algebra problem. Right? I mean, I'm not saying there aren't other things that think computationally, but at the end of the day, the actual computation ends up happening in the algebra world. And so I think that this should be one that shouldn't be too scared about computation. It should be possible. We've made categories in algebra, we should be able to do some computing. However, the things that we're computing are actually programs, little proofs, certificates that this is characteristic, that sort of thing. So you have to go into this world of proofs as programs, which is sort of a mantra you find on the internet for people who are sort of really big on like functional programming and stuff like that. Something called the Curry-Howard correspondence. And you know, it says roughly that a sufficiently precise proof is indistinguishable from a program. And if you've ever had to work through all the steps of something like the division algorithm for a student, you realize you are writing a little program. Okay? You have to put in more steps than people want, and there's limits to that. You know, start throwing in inaccessible cardinals or something, and that starts to break down. But the Curry-Howard isomorphism is a roughly true statement about proofs being programs. So that's what we're trying to use. So we're trying to say that the proof side of the world is going to move into a program side of the world. And there are programming languages that are designed around this. We're prototyping in Agda for reasons. And here's what it looks like. Oh, man, I should have known what's in my slides. The code from before, if you go to Magma, one of the computer algebra systems that many of you may have used, GAP has a similar format, you can ask it questions like, give me a characteristic subgroup of some kind. So this is a large matrix group project. You can ask for some subgroup, and it comes back as 2 answers. What do you think that iota was? It was the embedding. And that's because everybody who's computed has known that I'm going to do something inside to change the representation for efficiency reasons. I'm not actually giving you a subset of anything. I'm giving you other data stored in a different place in memory, a different file, and then I'm going to give you some program that'll translate that data back into your group. There were always embedding. We were never taking subspaces, right? And so this is just recognizing that we kind of already knew this. I'm trying to take credit for what we already knew, that's fine. But now we're trying to add the functor aspects. It has to apply to homomorphism, it has to have the natural transformation, and that's what it starts to look like in a standard programming language of this kind. It's always functional, everything's written differently, it's a little bit mathematical, but a little bit frustrating. For example, you don't find a for loop in this type of programming language. You don't find an if then else. In fact, you're not allowed to have any data at all. Everything has to be a statement that somehow has constants everywhere. And the data comes from the user only, not, it's very different, stateless programming. But anyway, you get used to it and you start to read it and a little bit of mathematics comes out, so it's not impenetrable. If you want to go into this world as adults, you can do that. Here's a hint that it's not totally trivial. We are not using the world's cheapest type theory. We're using homotopy types. We have to do these things called higher inductive types. These are hot off the press. These were invented back in 2016, and they're still being refined. Observational type theory is another approach that might work for this. We don't really know. We're not the best at type theory. We're doing what we can. This is a proof-checking software system. It's completely online. You install nothing. You write words, like you find in your textbook. You can see where the code's at. You can change it. You can check to see if you're right. And it'll check, and if you're wrong, it'll put a red box, but this one person has done it right. For my book, this is reasonable. I'm using this with undergraduates. I don't need lean for this kind of, teach them math the way I want math to be read to me and you. I think it's written down for humans. This is good for humans. The lean stuff, I really think, is a great place to go explore for a minute, bring back the tools that help you do new software, but if you're teaching, I encourage you to at least look at the scope of options before you jump in on any particularly hyped project. That's me off my soapbox. I'm done. Thank you, everybody.